Tonight we have a very special guest from the West Coast, Dominic Williams. He came in on the red eye from San Francisco, so he's probably about ready to crash, but really appreciate him with his effort to come tonight. Dominic is the CTO of String Labs and the chief scientist of DFINITY, and he's going to talk to us tonight about his project.
Thank you. So what you're going to see tonight is a presentation on an extension to the Ethereum ecosystem that provides a sort of scalable, decentralized cloud. The protocols, the decentralized network protocols that you'll hear about have been sort of in development, and the work's been bubbling away since the end of 2013. It would have surfaced in 2014 with a scalable cryptocurrency called Pebble. And at that time, though, the climate in the valley was, and it still pretty is, very Bitcoin focused. So, and Ethereum came out and so on. So, timing wasn't right. But the research continued, and eventually became DFINITY. And so finally here we are. It looks like it's gonna happen. DFINITY is a decentralized cloud, and you're going to get a brief tour of what it is. So first of all, our mission. The mission is to extend the Ethereum ecosystem with this cloud network. Two comparisons to see how they're the same and where the differences are. Currently, we've got something called Casper in the Ethereum world, and this favors what I'd call extreme availability. So the idea is that even if 90% of the network, the miners disappear, Ethereum keeps on going. In case of DFINITY, we can lose 40% of the miners before it stops, right? But we favor scaling, providing unlimited capacity, speed, and interoperability between private clouds and public clouds. Ethereum is ungoverned, and there's this idea that code is law, right? You can put these smart contracts up onto Ethereum, and nobody can stop you or mess with these contracts. DFINITY is governed. Now, it's not governed by people. We have a kind of decentralized intelligence mechanism, right, which we'll get to, called the blockchain nervous system. But the code is law is now contingent upon the wishes, right, and the decisions of this blockchain nervous system. DFINITY is going to be a boon to Ethereum, and I'll explain why. So if you think back to the 1990s, if you can remember, we had all these different hardware platforms, these different machines, right? We had, Spark from Sun, we had PowerPC, the old Macintosh used that, and then we had 8086. And 8086 proved much more popular because compatibility is popular, right? You had a choice. You had a laptop, you had your Dell, you got fed up with your Dell laptop, you could go and get a ThinkPad laptop and so on, right? So, in the coming virtual machine battles, we're expecting a similar effect for the EVM. We think that compatibility will be more popular again. So, we're going to support the EVM. You've got the code is law, and now you're going to have the decentralized cloud too. So developers can think, well, if I'm going to choose an ecosystem, I can choose to go to Hyperledger, Chain, R3 or whatever, or I can go to this more open ecosystem and I can put it on Ethereum where the code is law. If I don't like that, or I want these different performance properties and governance, I can just move that application and I can put it onto the decentralized cloud. And that strengthens the ecosystem enormously. So there's a foundation. Ethereum pioneered this. We've got a DFINITY Stiftung in Zurich, fully tax exempt, it's the first one. And our objectives are to enable decentralized cloud computing, promote compatibility for dApp developers, so you can just take a dApp, move it around, advance the Ethereum ecosystem, and that means funding and advancing core Ethereum technologies we're interested in, such as the Ethereum virtual machines, Solidity, state channels, that kind of thing, while also funding and advancing novel DFINITY technologies, which include things like these things we call Crypto 3 protocols and the blockchain nervous system. The project has been incubated by a company called String Labs, which is based in Palo Alto, which aims to kind of invest in and incubate open protocols. So DFINITY, core vision, it's in many ways the same, but there's some differences. The vision is a revolutionary limitless virtual computer. So we want to have a virtual computer without limits. And that's created by a decentralized protocol rather than servers. And this is an important distinction. So when you go to Amazon Web Services and you go to virtual computer, that virtual computer is backed by a physical server computer, right? It may be that there are 10 virtual computers, or instances as they call them, on a single computer, but nonetheless it's backed by a computer. The critical difference here is that there aren't any servers. The virtual machine is being created by protocol execution, right? So you've got a thing like Morse code, just a series of beeps that is being spoken between these clients, obviously a far more advanced protocol than the Morse code. And as a consequence of this protocol, we produce this virtual computer. The question is, why would anyone want the decentralized cloud? Hasn't Amazon Web Services got this all stitched up? And the answer is no, actually not at all. And the reason the decentralized cloud will be, in my view, dominant eventually is because it saves costs. Now, before I revisit that statement, I'll first make an admission, which is that, of course, the decentralized cloud is extraordinarily complex and will involve, 100+ times more computation than Amazon Web Services, right? DFINITY Cloud is going to involve 100 times plus, maybe 200 times the computational processing, right, than Amazon Web Services. Well, yet it saves loads of money. Why? The answer is actually simple. Here we can see, you've got the Amazon Web Services type solution, and you've got this thin little slither of computation in the cost. But then you've got all this human capital being applied. Whereas in the decentralized cloud, you're going to see a lot more computation, but a lot less human capital. And I'll explain why. Imagine that you wanted to create a financial exchange. So you're going to use the traditional cloud. Actually, you'll probably be scared of using the traditional cloud because it's not secure enough. You're probably going to get a custom cage in a hosting center. But just say you're going to use the conventional cloud. So, you've got a bunch of problems. First of all, you're going to be assembling all these different components, right? Then you're going to go and get these systems administrators to make sure that these components provide the redundancy and robustness that you need. You've got to have a disaster recovery plan, continuity plan, right? So you've got all these systems administrators and developers, and then you've got to get some security administrators, because if someone logs into your private, setup, right? If I can get onto the database, I can just go, get the command prompt and go drop star, right? And all your tables get dropped. No one will even know I've done it. So you need to have all these security admins, you need to have policies, and once you've got all those people, you need to have, HR people to make sure they're looked after, right? And then you're going to need managers, and then you're going to need payroll, and it just keeps on mushrooming out, right? Whereas, as we'll see, with the decentralized cloud, not only is the build process way simpler, you're going to be able to take some standard exchange from GitHub, make some minimal customizations, upload it onto the decentralized cloud. Not only is the development of the exchange much less expensive, but you also don't need all those systems administrators and security administrators and all the rest of it to support them, right? And that's why, in my view, you're going to see people moving to the decentralized cloud to save costs. Let's just quickly recap some of the ideas here. Why am I saying the development costs will be less? Well, here's a kind of example. I'd say IT systems shouldn't be Rube Goldberg machines, right? And unfortunately, for whatever reason, IT people have a habit of constructing all these Rube Goldberg machines. And this is why all these IT projects go wrong. You can talk about, some passport database in the UK that is really quite simple, and yet after 2 or 3 years, it's abandoned with $10 billion costs, right? So now, today you've got someone who'll love Amazon Web Services, and they'll become a specialist in all these different sort of special services and components that Amazon provides. And by the way, I'm only showing a fraction of the different pieces that Amazon gives you, right? And you can probably see there are quite a lot. So now, what happens is, your IT guy goes in and he weaves all these, he makes his personal selection of these components and he weaves them together with his custom code, and you end up with some hugely bespoke thing that nobody really understands, so you better have more than one IT administrator and developer in case they leave, right? Because no one else understands it. And of course, it's a kind of Rube Goldberg machine. There's all these moving parts, and it's very difficult to actually foresee how all these different components will interact. And that's what you get, a Rube Goldberg machine. It's expensive to build, expensive to maintain, expensive to keep secure, right? So, abstraction wins. In the decentralized cloud, you won't have any components, really. You're just going to have APIs. And, this is something called Instant DApp IDE we produce at String Labs. But, you've got a smart contract, right, which has got an interface. In the same project, you've got your user interface code. But the user interface code doesn't have any concept of a server, right? It just says, in this case, this is just the standard demo, var meta equals metacoin.deployed. And then you're saying meta.getBalance or meta.sendCoin, right? You're just programming the smart contract objects as though they were right there in the user interface. There's no concept, these are remote objects, or that there has to be a database server to look after the data. These objects just persist automatically, right? Way simpler. Got rid of all these components and distribution, and the system scales for you, right? You don't have to worry about scaling anymore. So, you've got no database, no scaling, just simple UX and business logic, right? And this alone will already make things much cheaper because the R&D becomes vastly simpler. And of course, when you end up with a simpler system, the maintenance of the system becomes vastly simpler. The decentralized cloud gives you a bunch of rather wonderful properties. First of all, you can create autonomous systems without dependencies. And this enables the creation of a completely new kind of system, right? It's simple, so you can have, you just code the processing rather than all these components. You don't have to build Rube Goldberg machines. The systems we create are shareable. We can, share code and governance, so you can create these autonomous systems that have kind of DAOs that make the system self-updating, right? It can adopt new code, right? It's verifiable. You know what code you interact with. This is hugely important, so people can put systems up there and, share them, and they all know that they know what they're using. They can go and look at the code on GitHub, right? It's like a guarantee. Now, the platform itself, of course, is unstoppable because there are no servers to fail, right? Once you get rid of the servers, there are no servers to fail, so it's unstoppable. It's tamper-proof. Why is it tamper-proof? Because there are no servers to meddle with. You can't get a command prompt on a server that doesn't exist, right? It's interoperable, right? The systems you build on the decentralized cloud are interoperable. There's no server boundaries. There's no machine boundaries. There's no concept of separate machines. We've just got these software objects that, depending on the permissions that the developer has set up, can access other software objects. All of these physical limitations, which we're used to, are removed. And of course, controversially, there's no servers, so the public decentralized cloud, of course, doesn't have a geography. It's just cyberspace, right? You can put a system up there, and it doesn't have a geography. And that's very useful for example, a lot of international businesses want to create these international financial rails that are outside of regulatory scopes. And so each company or user interacting with the system, of course, exists as a physical person in a regulated jurisdiction. They're regulated, but why should the protocol that connects them be regulated? It shouldn't be. So, this is where I think there's there's a lot of tally with the Ethereum vision. We want to see these core public services decentralized. And generic business systems and their data should be sort of embedded as protocols within the fabric of the internet. Things like Twitter, eBay, Uber, they shouldn't be separate companies. They should be these self-updating systems embedded within the fabric of the internet. The internet should do these things. It's not necessary for them to be managed in data centers by companies. And they'll develop much quicker. Look at eBay, right? How often does the eBay website change? Well, think about Gmail. It was great when it first came out and you had Gmail Labs. And for the first couple of years, you had all these extra widgets, and then, development kind of stopped. And this is why, actually DFINITY was founded. Pebble kind of came to an end and became DFINITY. The objective was provide the massive scalability for things like the sharing economy, microblogging, mass messaging, search. This is a surprising one, right? So we think rather differently to most of the blockchain industry. One of the requirements for the beginning was, how can we have a decentralized Google on the virtual machine? And partly that was just for enjoyment. It's a very interesting technical challenge, but as we'll see later on, it's not nearly as impractical as you might think. Storage obviously easy. So this system can also enable just more conventional root level business re-engineering. You can combine a DFINITY public cloud with interoperable private DFINITY cloud computing networks. And this is very important. Supply chain and trade finance, medical records, voting and governance systems, collaboration economy, and it just goes on and on, auditing and compliance. So many things that can be re-engineered using this kind of technology. The other one for us is a big one. So there's only actually two projects in incubation at String Labs at the moment. One is DFINITY. The other one's a thing called Phi. And we want to do decentralization of core societal functions. So Phi is what we call decentralized commercial banking, although it's not a bank in sight, obviously. And this system uses properties of DFINITY, specifically its ability to produce unmanipulable and unpredictable random values to give out loans algorithmically. So we've got economists looking at this, and the general conclusion is that the algorithmic system that works without a bank gives out loans much more judiciously than banks do. They can obviously do it at a fraction of the cost. Banks are very expensive. Those are the kind of three applications we see of DFINITY. Scale out. You basically have a network of DFINITY mining clients running these Crypto 3 protocols, and a virtual computer is formed from protocol interactions, and you get a virtual computer with some kind of storage capacity and some kind of processing capacity. The difference is here, where new clients join the network, the capacity of the virtual computer grows, and it can do that indefinitely. And so we want to produce a virtual computer of unlimited size and capacity. Blockchain nervous system, this is a key difference with Ethereum at the moment. I'm talking about extending the Ethereum ecosystem and giving people different options depending on their particular needs. It's decentralized governance. How does it work? So Coder's law is now contingent upon a decentralized intelligence, and the governance system uses privileged machine instructions. Actually, it's very surprisingly easy to implement this, right? All you need to do is go into the EVM, add a few extra instructions. It's a bit like the step from 286 machine to 386 when you've got like privileged, protected mode instructions and stuff, right, for the operating system. You add the instructions into the EVM. You don't even have to, by the way, for the smart contracts, the smart contract component of it, you don't even have to recompile Solidity. Because in Solidity, curly braces, right, now you can just put the opcodes in directly, and I think it's like percentage sign, and you can just specify the opcode by number, right? A lot of this stuff's actually much easier than people realize. Anyway, so here we've got the virtual computer, here's the state, corrupt system or data, and here comes the blockchain nervous system, and it zaps it, it freezes it or fixes it using privileged opcodes. So what are the kind of purposes of this thing? We can fix deadlocks, we can mitigate hacks, we can return stolen funds, protocol upgrades, freeze vice or violence, and we'll get to how this thing makes decisions in a while, and configuration. So let me just give you some examples quickly before we move on. Protocol upgrades. Another key difference with Ethereum, we have no concept of a hard fork. No concept of a hard fork, this ridiculous thing. So if you can imagine, you know what a parity is, right, in Geth? You get these Ethereum clients. So you can imagine wrapping those with a proxy, right? And the clients, the users, talk to the proxy, right? The proxy, meanwhile, is aware of the decisions of the blockchain nervous system. The blockchain nervous system says, hey, we're upgrading the protocol, and here is the hash of the new client, right? The wrapper pulls the new client down off some decentralized network, such as IPFS or BitTorrent, installs the new client, or depowers the old one, installs the new one. You can do that without actually really interrupting the user at all. So, our ambition is to hard fork at least once a day, and nobody even knows it's happened, right? What a ridiculous thing a hard fork is. There's so many ideas that come from Bitcoin world that are utterly absurd, that we don't even know are absurd, right? So, no concept of a hard fork in DFINITY. It continuously upgrades the protocol, and the users of the DFINITY cloud aren't even aware this is happening. Configuration, some other differences. So things like mining rewards. In order to create a mining client, you have to create an identity. To create the identity, you have to make a cryptocurrency deposit, right? DFINITY's deposit. What should that deposit be? Because after all, the value of a DFINITY might be volatile. Well, guess what? The blockchain nervous system decides. So get rid of continuous issuance algorithms, the idea of which again came from Bitcoin. Well, that's gone. So, we're talking about really, really fundamental differences here once you introduce the blockchain nervous system. Public-private cloud interoperability, and this is made possible by these Crypto 3 protocols. Basically, people can run their own private clouds, and they've got software systems on those private clouds. And those software systems on the private cloud can call into the software system on the public cloud. In this thing called the Zinc release, it's going to be quite simple. And it's actually complex to go further than this, so I don't know how long this will be around for. But you can have a top-level private method in a smart contract on the private cloud. It can be twinned with a single call to the public system. But this is really important, right? Because you could have a supply chain on the private cloud, right? You can have a function like, buy, your parameters, product code, quantity, price, recipient, blah, right? And now you can twin that by decorating it in Solidity with a call to, for example, send some kind of stable coin that exists on the public network, right? So corporates can now build quickly using open business systems, right? Like software libraries. And you can build your system on your private cloud by incorporating all this functionality on the public cloud as though you're on the same machine even though you're not. And so, for example, if you can imagine some big corporation with a supply chain network for trade financing, and they might want to incorporate a stable coin, identity arbitration. You might, different private chains want to interact via an exchange. So here we've got two private networks, and there's a public service on the public cloud. This could be a carbon credits exchange, right? So, one private network produces a carbon credit, the other private network consumes the carbon credit. It's really important to enable people to connect because then you get network effects, right? Network effects are really important. Okay, so I'm going to give you, there's a ton of theory. We couldn't even scratch the surface, really. So what we're going to do is we're going to examine some of the sort of most fundamental kind of principles that we use. The most fundamental thing in DFINITY is randomness. Everything we do is driven by randomness. The production of random numbers is by far the most powerful thing you have in the creation of both decentralized protocols and networks, and also high-level applications like decentralized banking, Fi. So we'll see how we produce random values. We'll see how we produce a blockchain from this that has better security properties and better performance properties than anything ever seen before. And this will kind of give, I think, a reflection of the kind of ways we do things. Look at some quick applications of randomness. Look at how the blockchain nervous system works. Look at some public-private interoperability in a bit more detail. These two things these first two sections are going to be more technical. I think most people can understand what follows, right? It gets less technical. So if you can kind of withstand the first bit, right, then you're going to be sort of like relieved, and it's going to be easier and easier as it goes on. Okay, so threshold relay, unmanipulable, unpredictable randomness on demand in decentralized networks. And as this guy says here, this is the crypto 3 technique you need to know about first. It's called threshold relay. So the protocol design challenge is how do you organize 1 million plus mining clients to produce one massive virtual computer, the DFINITY cloud? So actually when the DFINITY project started, the basic requirement was that all protocols had to be usable in this system, this network that would have 1 million plus mining clients. Why do you need to have a million plus mining clients? Well, Google Cloud Platform has more than 1 million servers, right? Microsoft has more than 1 million servers, right? So that's the kind of numbers we're talking about. You probably need more than 1 million, right? Let's start with randomness. So just reflecting on proof of work for a moment, randomness is already the fundamental engine used to derive stateful decentralized networks. A stateful decentralized network is something like Bitcoin or Ethereum, which remembers the state, right? Like BitTorrent doesn't remember it, but in Bitcoin you've got this virtual ledger. If I put some Bitcoin up there that's freely spendable, one of you spends it, the rest of you can't, etc. So proof of work is actually a very, very simple thing. Miners race to solve a current puzzle, which is just basically creating a block with spinning the nonce so the hash of this block is below a target. They race to solve this puzzle you can only solve by brute force, and the solutions are found randomly in a Poisson distribution, which is very problematic, but it worked. It was a breakthrough in 2008. The winner of this race to solve the current puzzle can append a block to the blockchain. And in effect, this winner of the race to solve the puzzle was a temporary leader. And the nice thing is the next leader is unknown. It's unpredictable. It's a random selection. So you can't do a denial of service against the leader because you don't know who the leader is going to be. And you'll notice, by the way, there are lots of decentralized networks out there at the moment, especially in the proof of stake arena, where you have a leader. And not only do you have a leader, but the leader's predictable. So someone like me who really understands how these protocols work just destroy those networks very easily, because you can just identify the leader and then just attack the leader, and then they deterministically choose the next leader. So of course, if you've got things set up, you're going to move on to the next leader. That's why Satoshi used this approach. Obviously, if you don't know who the next leader is, you can't even manipulate them. You can't do anything. So long as there's an honest majority, so as long as there's an honest majority of the computing power is held by what we call distributed computing, correct processes, the chain functions correctly, and the adversary cannot control the chain. So all of this is possible simply because this race to solve this puzzle by brute force results in the random selection of leaders. Otherwise, there'd be no Bitcoin, there'd be no Ethereum. Randomness is at the core of decentralized networking, and it's actually much, much more important than anybody realizes. Okay, what does a DFINITY network look like? Well, just so you know the terminology, because it sort of comes from distributed computing. Mining client software in DFINITY speak is a process, right? So you hear me talking about mining clients and processes interchangeably. They mean the same thing. In DFINITY, each of these mining clients has to supply a certain amount of computational resource, right? And we have various cryptography that ensures they are actually supplying that computational resource. They're organized in a P2P broadcast network. So again, a lot of these protocols out there at the moment require point-to-point communication. And I mean, without getting into details, you can probably see there's a bit of a risk of a DOS attack, right? If you can directly attack mining clients, it's very risky. So, you know, we have P2P broadcast networks, and you can scale P2P broadcast networks by sharding them all sorts. You can gossip-based, organize it using academically structure, whatever. Each process is a mining identity, right? A mining identity is, you know, just a usual, like an EA account identity or something like that. It's a public key with metadata attached, basically, that's recorded on the ledger. Ownership of these IDs mediate participation. If you want your mining client to join the network, you need a mining identity. So on a private network, you have a trusted dealer, right? Systems administrator. Like if a bunch of banks want to run their own decentralized private cloud, they're going to have some association with some guy who collects all these identities, right? And they're going to be like, the trusted dealer is going to give out the identities are going to be configured on these different computers, and then the private cloud is going to come into being. And in that sense, there's no issue about Sybil resistance. In a public network, of course, it's completely open. Anyone can join. So how you mediate it by requiring people create a cryptocurrency deposit they have to make a cryptocurrency deposit to create the identity. We also have something called USIDs. We won't cover, or we could do it in questions if you like, unique state copy identifiers, which is a semi-hardware based mechanism by which we hold identities to their roles. The network size, obviously, and DFINITY network's massive. So these processes in our massive network are organized into random groups. Each group has random members. Each process, mining client, is a member of multiple groups. Groups intersect. In the DFINITY network currently, the design is we have 400 members. And the groups set up something called threshold cryptography. Don't worry, it's not bad, right? So you know what a signature is, right? Who here knows what a digital signature is? Right, it's like if you have a public key, you've got a private key, you can sign a message, and everyone can verify that that message was created by the owner of your public key. So you can do the same thing with a group. So you have a group of 400 processes, and you need some proportion of that group to collaborate in order to sign a message. And the group gets a single public key that anybody can use to verify that the group created the signature on the message. And surprise, surprise, we set our threshold at 51%. 201 out of 400 are needed to create a signature. And they do this, by the way, it's very simple. Like, the message comes along, the group needs to create a signature. The members of the group create a signature share, right? A signature share on the message, and they broadcast it. And if you collect enough of these signature shares, you can combine it to make the signature, right? So if you had a group of 400, some message comes along and they have to sign it. If 201 or more agree to create the group signature, they make these signature shares, broadcast it. All you need to do is collect 201 of these signature shares, and you can make a group signature, a threshold signature on that message, right? Here's the magic. So there's a guy called Dan Bonnet at Stanford. I live next to Stanford, and I was lucky enough to find out about it, but I was seeking this algorithm. It's kind of magic. This thing called BLS signature scheme. Math magic, right? So now we have all these groups, right, with a single public key registered on the ledger. Here's the magic. The group needs to sign a message. They create signature shares on the message and they broadcast it. If you collect 201, you're going to make the signature, right? The group signature. The magic is, it doesn't matter from which 201 members of the group you collect those signature shares from. The output signature of the group is always exactly the same. It's unique and deterministic. It doesn't matter. The signature shares will all be different, right? Doesn't matter, though, which 201 you collect signature shares from. When you combine them, the output threshold signature will always be exactly the same, which, if you notice, gives us something without consensus. If 51% of the group agrees, they just broadcast their signature shares, and now these things can be combined by anybody. It doesn't matter. You don't have to organize which signature shares we're combining. You just have to collect 201 of these signature shares. Now you can combine them to produce this threshold signature, which, by the way, is a random number, right? It has to be a random number, otherwise it would be insecure, predictable, wouldn't be a secure system, right? And it's always the same. So now we've got a stepping stone, right? We've got a stepping stone to something much, much more powerful. So you can now use that random number created by the group to select the next group. This is very, very simple. We can just take that random number, remember the signature is a random number, modulo it by the length of the list of groups, use that as an index to get the next group. The next group uses the previous group signature as the message. Well, you can see this goes on ad infinitum, and the sequence is entirely deterministic. There's no manipulation possible, right? Because the group is always signing the previous group's signature, right? And the result of the group signing is, there's only one possible signature because it's unique and deterministic. There's no I'm going to withhold my signature to change the randomness and select another group or anything like that, because there is only one possible signature that the group can ever produce on any message. So what we get is something called a verifiable random function, and it's producing these numbers that are verifiable using the group keys. Anybody in the network can say, yeah, this group produced this random number correctly because it verifies against the public key, which is pre-committed to. And the values are produced on threshold agreement. It's so long as 51% of the group is ready to proceed, it produces the new random number. It's unmanipulable and totally unpredictable. Here we have the first group, right? And it's basically, it was selected by the previous group signature. This group at a block height h-1 uses the previous signature as a message, creates a BLS threshold signature on it, right, using the signature shares for its members. This creates, the output signature selects the next group at block height h, which then uses the previous signature as a message, produces a new threshold signature, a new random number, unmanipulable, unpredictable, and this just continues ad infinitum, right, forever. So now we have this unmanipulable, unpredictable sequence. So the question now is, okay, this sounds pretty fucking cool, right? We can have something much more powerful than has ever been seen before. What is the communications overhead and processing overhead, and what is the fault resilience? What are the fault bounds? Okay, so when these group members want to sign a message, they have to create some kind of protocol message. It's going to have their ID, that's 20 bytes, like a standard Ethereum address, right? They're going to create the signature share, BLS signature shares, 32 bytes. And they're going to sign the communications, it's another 32 bytes. Total 84 bytes. So each process in the group, 400 processes, broadcasts this 84-byte message, and group size 400, threshold 201. How much communication overhead is there? Well, the maximum it can be, 84 times 400, is 34 kilobytes. But guess what? Once you only need 17 kilobytes to make the threshold signature, and of course once that's created and broadcast, everyone stops relaying these share messages. So in fact, you get about 22 kilobytes of message transmission. 20 kilobytes of message transmission. 20 kilos is nothing. It's just not even worth thinking about, right? And yet it produces this unmanipulable, unpredictable randomness. As we can see, it's almost incorruptible. So let's imagine a smaller network of 10,000 processes, of which somehow 3,000 have become faulty. Now, this is a pretty disastrous situation, right? With professional mining, people have put down security deposits and so on. This is not really an adversary, probably. This is more likely a network outage, right? Some kind of widespread network outage. So obviously, if you've got 3,000 faulty, this is just like a distributed computing terminology. You say that processes that aren't working properly, they can behave arbitrarily and they're faulty. 7,000 correct processes, group size 400, threshold 201. What is the probability that 200 more processes in this randomly selected group are faulty, preventing the production of a signature? What is the probability? It's actually very easy to calculate. There's a thing called a hypergeometric probability, and there's calculators on the web. You can play around with the numbers. It's amazing. It's 10 to the minus 17. 10 to the minus 17. And this is because of the law of large numbers. So, when the internet was originally designed as a packet switching network, they were aware that as the number of nodes in this packet switching network increased, the packet switching network will become more and more efficient, right? And the reason is, although the flows of individuals are completely unpredictable, when you have a large enough number of unpredictable actors, the variance drops and it all becomes predictable. And this is the reason we're getting these insane numbers. I mean, if we increased it to 500, it'd be even more insane, right? It never fails, right? The only way it's going to fail is if you really knock out, say, 40% of the network. And my view is that when you get to that kind of situation, 40% of the internet's in an outage, that the system should stop. Better than doing the Bitcoin thing, right? Where you just, in Bitcoin, if there was hostilities, military hostilities in the South China Sea, both China and America have got cyber warfare kill switches, the internet links go down, Bitcoin's going to fork. You're one fork in China, one fork in America and the Western world. And when the diplomacy resolves it, one of those forks is going to collapse. We think that when you get to the point where there's that much of an outage, you should stop working. And to prevent that kind of risk, you have one, we're going to create a dragon chain in China, right? And there'll be another chain, and that's how you solve it. But anyways, you can see it doesn't fail. So now, this is, you can see some of how powerful this thing is. This is a thing called threshold relay blockchain. We're using a thing called probabilistic slot protocol, PSP. Don't worry about the terminology. It's not nearly as bad as it sounds. So when a group is selected, right, the members of the group start their stopwatches, right, and they're waiting for the expiry of the block time. Of course, here's the signature from the previous group that selected them. They're all going to receive the signature at slightly different times because they're all at different places in the network, and the network's got a delay diameter and so on. Doesn't matter. It's all right. It's all okay. They've started the stopwatches and they're waiting for the block time to expire. So once a group produces its random number and selects the next group, it also creates a priority list of what we call forgers, which the word I know is first used by NXT, right? There's a guy, Sergey over there, will remember this. And the list of forgers is a list of all the processes in the network that are just in a random order, right? And they're in slots. There's slot 0, slot 1, slot 2, slot 3. Just a random ordering of all the processes in the network. Here we have process 2313 is in slot 0, process 3493 is in slot 1, and so on. And we give them a kind of time after which they can publish their blocks, and the blocks nominally be ignored before that. If this is just a network optimization, if this isn't done, the system actually still works. So it's not dependent on these timings being stuck to. But anyway, here we have a block time of 5 seconds. So after 5 seconds has expired, those processes will accept a block from slot 0, the process in slot 0. After 6 seconds, they'll accept a block from slot 1, 2. After 7 seconds, from slot 2, 2. 8 seconds, slot 3, 2, and so on. Actually, you can have all the slots being able to produce up to 5 seconds. It still works. It's just an optimization. And this continues. At every block height, whatever the block height is, there's just a different random ordering of the processes, right? Just goes on ad infinitum, right? So whatever block height you're at, you've got a random ordering of the processes into these slots. So chain choice rules, very, very simple. Correct processes always try to build on the highest scoring chain, right? So we also award scores to blocks from the different slots. A block from slot 0 is 1 point, a block from slot 1 is half a point, a block from slot 2 is a quarter of a point, a block from slot 3 is an eighth. And there are different trade-offs and numbers you can use, but this is the best in my opinion. So here we've got a chain that's at H that's rooted in slot 0, and then it's forked, right? And we've got blocks at slot 0 and slot 1, and then somehow it's continued, and you've got the green chain and the orange chain. So, if you wanted to choose the best parent and you were a correct process, well, you'd just, calculate the score, and you'd see that from the common root, the green chain is plus 4 points, the orange chain is plus 2 3/4 points, and that's, if you're a correct process, you'd choose the green chain is the highest scoring. If we just did this, we'd have all these problems with selfish mining, nothing at stake, all the problems that you get in things like Casper that it's trying to solve with betting and so on and slashing. But we have another very powerful weapon that comes from our group threshold abilities, and it's called threshold block notarization. So now the group does something else. Each member of the group, right, will sign blocks that it sees, until it sees that the threshold group has created a signature on at least one block, at which point it moves on. They sign the randomness and relay to the next group. But until they've seen a block, they just keep on signing blocks. But they have this rule: if you receive a block, right, at height h from some other process, you ask the question, have you signed a high scoring chain before? Otherwise, there's no point in signing it. If you haven't, is that block valid and the piece slot ready? If so, you just broadcast a signature share on that block, right? And you just keep on doing this, right? And when you see that your group has successfully signed some block, at least one block, you just broadcast your signature share on the randomness now and relay to the next group. Now, something you should notice, of course, with this, before the block time expires, of course, those processes are just putting the blocks they're receiving in a priority queue. So if a block is received from slot 0, it's going to be placed at the top of that priority queue, right? So when it moves on, all it's going to do is sign slot 0 and nothing else, right? Group members only sign the highest priority block from the queue signed so far. So they're just going to sign slot 0, and that's me done. I'm just going to wait until I see a signature on slot 0's block. So most of the time, you're only ever going to sign slot 0. That's the normal expected situation, right? And if for some reason, because there's a synchrony, you've got like a slot 0 is in America, slot 1 is in Europe, and they somehow both get enough signatures and they sort of cross mid-Atlantic and cables there or something like that, and the score of the chain goes down, right? The algorithm just lengthens the block time, right? To deal with the asynchrony, the algorithm lengthens the block time, right? A bit like, Bitcoin plays with the difficulty and so on. So now we see something rather wonderful happening. This notarization drives rapid convergence. You can only reference a previous block that has been signed by the group, right? So you just basically collapse those forks. And things like selfish mining are now impossible because there can't be a hidden chain anymore, right? There can't be a nothing at stake chain that someone can go back and create. Like the whole problem with all this proof of stake stuff is you can just go back in time if you've got the keys and just create alternative chains, right? There's nothing stopping you. There's no cost involved. Bitcoin deals with this problem using proof of work. Oh, well, since you're having to expend all this energy to create a block, it costs a lot of money to go back in time and create an alternative chain, but you can still do it, and that's why you have selfish mining. But in this system, of course, you don't have that problem. You certainly don't have nothing at stake, and you don't have the selfish mining thing. Each block can only reference a previous block that's been signed, notarized by the group, and you've seen the resilience of the group, right? The group, once it's created a block, it moves on. Now, there are some, weak kind of attacks, but you go through them and you see, wow, there's not really much you can do. So, what do we get from this? Threshold power. This shouldn't be timestamping benefits, that should be notarization benefits. Super fast during normal operation, you get an overwhelming probability of transaction irreversibility, i.e. finality, in 7.5 seconds. Having these threshold groups notarizing blocks resolves various security challenges, resolves nothing at stake. This has been a huge problem for years. That's gone. Equivocation, I won't explain that, but it's a more traditional distributed computing issue, resolved. In fact, we actually allow equivocation as part of the system. Selfish mining, right? Impossible, because you can't have a private chain that you're building on in secret, right? You can't withhold blocks because once the chance is gone, you can't get them notarized by the group. The group's moved on, too late, that block will never be valid. So we solve those problems. And obviously you can score the chains, so you have a kind of quantifiable risk, right? You can look at the chain, you can look at the blocks and the score of it, and you can look at the presence of multiple chains, multiple threshold signatures, all kinds of things, and you can basically get, kind of clear statistical risk. You can look at what you're seeing, and you can decide very accurately whether you should trust it. You can also do simple payment verification. I don't know if you've heard of this thing in Bitcoin where when you want to prove that something's been embedded in the Bitcoin chain, right, to somebody who doesn't have the Bitcoin chain, and you just create this kind of Merkle path to a block header, right, with a proof of work. And you can do exactly the same kind of thing with this threshold system. And the light client only has to have a Merkle root, a 20-byte Merkle root of the set of group keys, right? Group public keys. And from this, you can do SPV. So that's one of the other things that's been missing, right, in proof of stake. How do you do SPV? Well, actually, SPV here gives you better guarantees than Bitcoin. So this is the interesting thing. We've got all this performance, like 7.5 seconds finality, but we've also solved all these, security problems that bedevil, proof of work and proof of stake. We've got rid of nothing at stake, we've got rid of equivocation issues, and we've got rid of selfish mining. Just reflect for a moment on the problems of proof of work, because I've been not too happy with this algorithm for a long time. About the environmental cost, Bitcoin's predicted to consume as much electricity as Denmark by 2020, or Motherboard said that this year. Personally speaking, I find that a bit ridiculous, given the environment, the problems we've got. In the Ethereum network, there are some problems currently. Currently, 50% of the blocks being mined, or at least last time I looked, are empty. Right? They're empty. And it's proof of work's Poisson distribution that's to blame. And the reason is, the sooner you publish your block, right, with the Poisson distribution, the greater the chance is that somebody will build on top, and your block will make it into the chain and you'll get the reward. So you're thinking, well, okay, if I publish an empty block, the next guy is going to want to build on top of me because he doesn't have to delay and validate my transactions, right? He can just build on top. He's got a greater chance of. So basically, it turns out that the most profitable approach in Ethereum right now is just to broadcast empty blocks. And so that's why it's very important that Casper hurries up and gets itself into production, because at the moment, this is a serious problem, and this is one of the reasons that the gas limit on each block has been set so low. Right? It's been set so low to try and stop the miners doing this, right? Because the higher the gas limit, the worse this problem's going to be, the worse the delay, right? That you're going to, once you get rid of this horrendous Poisson distribution thing that's in proof of work, you can now, massively increase the throughput. This is without any kind of scaling technology, right? So if you look at block time and finality and so on, let's make a comparison. With Bitcoin, we have an average block time of around 10 minutes. As you know, it varies wildly. Some blocks take hours, some go in 20 seconds. On average, let's say 6 confirmations to finality, which means that transaction finality happens in an hour, true finality. Gas doesn't do any computation, right? It's just a ledger. Ethereum, block time, like 20 seconds. I haven't checked it out currently, but again, varies somewhat, much less. It varies wildly, but not nearly as much as Bitcoin. I should probably get rid of the wildly. 25 confirmations, that's pretty good finality. 6 minutes. Gas available, this tiny gas, you can hardly do any computation in a block because of this issue, right? Everyone wants to publish this block as quick as possible. DFINITY, block time, average 5 seconds, low variance. This is the really nice bit, though. I won't get into how you decide what finality is, but generally you need 2 confirmations. Average 7.5 seconds. So these are huge improvements we're seeing, which is, I suppose, what you'd expect to see in a new field of technology. But the reason this step is so important, going from 6 minutes to 7.5 seconds, is now you can create a good user experience. I was last year trying to create financial exchanges for a thing called mirror assets, which we abandoned for various reasons, on Ethereum, and we had these financial exchanges. I'm trying to explain to create ways of conveying to the trader how the results they're seeing can be reorganized, right? You can see your trade going through, and then the next minute, you don't have those assets, and it's all been rolled back. How do you visually show to the user that everything they're seeing in their application actually can be rolled back? It's a very, very difficult challenge. When you get to 7.5 seconds, and I think we can even make it faster, now you can start to give a much, much superior user experience, and you're sort of beginning to see that you can make this ready for prime time. Now we've got rid of the Poisson distribution. Obviously, Casper will get rid of the Poisson distribution too. You can now have much more gas. So even without any kind of scale-out technologies, you can now have 25 to 50x the computation, or maybe even more that Ethereum has, right? Because whoever the miner is in slot 0, if the block time's 5 seconds, if the delay diameter of the network's 2 seconds, which is the Bitcoin delay diameter, but it should be much less with this for various reasons, because we're not going to include China, have a separate chain. He's got 3 seconds to accumulate transactions and validate them and so on. He's not like racing to get his block out. Doesn't matter. If he's got the delay diameter is 2 seconds, he can do this for 3 seconds broadcast. If the delay diameter is 1 second, he can do this for 4 seconds of broadcast. The gas can be vastly higher. So we're talking about massive, massive improvements in performance. And this is even without any of the other technologies. So applications of randomness. So one of the other things that's so important about the system is that it produces this random heartbeat, right, which applications can use. So scale-out virtual computer, handling any volume of computation and state. This is what we want, right? We want a single virtual computer, the giant God mainframe in the sky, right, that can handle anything. So let's just think about this for a second. Going back to good old-fashioned computer science. We need to separate and decouple concerns. So if we go back to proof of work blockchain, we have this thing proof of work, and it muddles up all these things like validation, Sybil resistance, state storage, consensus. They're all kind of like intertwined in some kind of knot. Right? So what you need to do is you need to go to a different architecture where you have a kind of layer, consensus, validation, state storage, and Sybil resistance should be separated out. As you know, we have mediation, participation in a DFINITY cloud is performed by the ownership of these mining identities. In a private network, that's a trusted dealer. In a public network, you have these UCIDs and cryptocurrency deposits. Sybil resistance is separate, right? That's bundled in the identities. And then you've got the processing the network does, consensus, validation, state storage. And of course, this kind of thing's not original. If you think back to TCP/IP, you've got application, transport, internet, network access, right? There's a reason that we use layered architectures in distributed computing. It's so that we can decouple and separate the concerns so we can address them optimally. So this is basically what you see, and there's a bunch of things here I'm not going to try and explain right now, but you have this top-level consensus layer, which of course, guess what, is a threshold relay chain, right? It may not be the one you've just seen. There's a whole bunch of variations on it, but it is the threshold relay chain that produces this random beacon, right? And guess what? We don't store transactions. There's no concept of storing every transaction. This is an absurd notion, again, that's come from Bitcoin. We're talking about, systems that will have exabytes of state and maybe billions of transactions a second. Who is it that's going to record these transactions? How are we going to put them in a block? Very difficult, right? So the only thing you actually store in this top-level chain is a state root, 20 bytes, 20 bytes. It's all just a state root. Like a Merkle tree root, 20 bytes. Very lightweight. And you also store like metadata, like joining a new process, joining a new group, removing a group, whatever. So this top-level chain is very lightweight, just network metadata and state root. This random beacon drives something called a validation tree in the validation layer. And the validation tree is composed of things called validation towers. And they basically do for validation what a Merkle tree does for data. With a Merkle tree, I don't know how many of you know what a Merkle tree is, but you can, Factom, right? These Merkle trees. You can have any size of input set, and you can put a Merkle tree over it and get a single hash root out, right? And you can anchor everything. You can notarize all of that data with a single 20-byte root hash. So we have a similar thing called a validation tree. Obviously, probably a lot more complex, right? But it does the same kind of thing for global validation, because one of the great misconceptions at the moment in the blockchain space is this idea that you can just have lots and lots of different chains and you can link them all together somehow, right? And then somehow one chain can produce some token or some kind of computation, and somehow you can pass it across to another chain. The problem with that is that if one of those chains, you just reduce the security. If one of those chains, if you're an attacker, you just target one chain, and now you export bad data, right, from that chain you've compromised, which is obviously much less secure than the network as a whole. So actually, it doesn't really work. And you see a lot of people talking about this. Unfortunately, it's theoretically unsound. It doesn't work. You need to have global validation, right? Global validation. There's no escape from it. It is tricky to do, and you do need randomness, and you do need some extra theoretical techniques, but it's absolutely necessary to do it. So that's why we have this single global validation layer that can validate any number of state transitions from the storage layer at the bottom, right? So transactions come in that involve some computation. It's slightly more complex in DFINITY. These things are going to be able to roll across multiple blocks, but anyway. And these, the resulting changes to state and the data involved gets passed up to a validation tower. Eventually it produces a digest, and other validation towers validate the outputs of other validation towers and so on, and eventually you get this state root. The validation towers can proceed synchronously. It's not like, you go the speed of the slowest validation tower, right? The thing just moves independently. So other example applications of randomness, that's the thing we just talked about, a validation tower. I'm not going to try and explain it. Validate network state changes using a few processes with the same level of security. You can, the whole network could validate something. Lazy validation, right? So I mentioned at the beginning I want to have like a search engine. That was one of the original objectives, to put a search engine, to centralize Google onto the public cloud. Well, now of course you can see all the Bitcoin guys going, it takes a long time to validate stuff. Well, that's true. You've got a validation tower and so on, or whatever. And the danger is that, there'll be some miners out there who are crooked if you don't do any validation, right? They're going to insert search results, insert advertising into the search results. That wouldn't be any good, right? Or sort of like, miners supplementing their mining incomes by inserting advertising into the search results. How do we solve this? Because validation takes a long time. You can just do something called lazy validation. These are low cost, low value, operations. So now you have a system where, search results are returned immediately, the miner retains them, and then randomly the beacon selects them to be validated. I don't know, let's say 1 in 1,000 times. Now, the reason that the miner won't want to put advertising search results into, return invalid results, is that if he can't prove, if the random beacon selects him, he can't manipulate it. If he selects him and says, validate that you did this correctly, if he can't prove that he did it correctly, well, he's going to be frozen out, and he's got, this kind of expensive, mining identity, right? With all this unpaid mining rewards and the security deposit and various other things, right? And for what? Making a small amount of money by inserting some stupid search results, advertising into the search results. So, that's one example. Lazy validation, the random beacon enables you to do that. Now you can produce instant search results, right? Another problem, right? With a decentralized cloud, everything costs something, right? There's no free computation, otherwise, it would be DOSed. But it's a very, very small amount of payment. If you make a search, it's going to, hundredths of a cent or something, right? It's not going to cost much. But the trouble is that, you have to validate even small financial transactions. Because, even though a transaction may be very small individually, right, you can combine zillions of tiny transactions to make a big fraud. So actually every single transaction involving the transfer of, inverted commas, money has to be validated. How do we deal with that? Because it's expensive, validation tower, all this kind of stuff. So again, we use the random beacon, right? What we do, for example, is we say, okay, the cost of performing a web search is now 1,000 times greater, right? So if it's 1/100 of a cent, it's now 10 cents, whatever, 10 cents to perform a web search. Well, that's not very good. Most users aren't going to be able to forget about the cost if it costs 10 cents to do a web search. No worries. Guess what? You only get charged the 10 cents 1 in 1,000 times. The random beacon does it, right? So now, 999 times, we don't have to do any validation of the search, because the random beacon is taking care of it for us, right? It's called lottery charging. So it's amazing what you can do with randomness. The final example, I won't try and explain the whole thing about Phi. Phi basically creates a stable currency which is secured on loan collateral, and it gives out loans algorithmically. This is a kind of extract from the DevCon 2 presentation, Decentralized Commercial Banking and Stable Currency. Basically, you get these human validators, right? Which is, it's like being a miner, right? These are loan miners, if you want to call them that. And their job is to basically to tell the computer, right, whether it should give out a loan. So they make it a security deposit, which is used to hold them in various sort of game theoretic ways to making good decisions. How does the computer issue loans? Basically, you got to these are like a chain of validators. There's a proposer, and if he agrees to the request, he tells the computer, commits to the hash of the loan application, which is in a standard format. The computer then randomly chooses another validator. He'll check it, tells the proposer, please encrypt the loan application to the public key of the next validator. It's uploaded. The next guy looks at it. and so on. Now, there's a random sequence of validators. Nobody knows who's next. Nobody knows how long this sequence of validators will be. Choice of validators depends on the size of the deposit and reputation and so on. And then eventually, if phi, decides that it's been validated, it just creates the phi, and for various reasons it's stable beyond what we can discuss here, and it issues the loan. So, there's some validator incentives and so on relating to interest they might receive if the loan goes through, but also the kind of they get penalized, they kind of underwrite it. But anyway, the amazing thing is with this system that it's actually able to give out these loans judiciously, right? I mean, economists who looked at this stuff and said, yeah, we think it's probably more judicious. Not just probably more, like probably much more judicious than a commercial bank, right? And it's just an algorithm, right? Using random numbers. That's why pure randomness, like genuinely unmanipulable, unpredictable randomness, is the single most powerful thing in decentralized networking, right? Incredible things are possible using random numbers. Okay, so now we can get less technical, away from randomness and threshold relay and probabilistic slot protocols and so on, and get onto the blockchain nervous system. So this is the decentralized governance, and we kind of cover this, right? This is how it works. People can submit proposals, right? There are standard types of proposal. You have to pay a fee in DFINITYs to create the proposal. Otherwise, you could DOS the network, right? You stick it into the blockchain nervous system, smart contracts. But there's also, the real blockchain nervous system exists off-chain, right? It's composed of neuron client software, which we'll get to in a second. The blockchain nervous system evaluates the proposal. The process is dependent on the type of proposal, obviously, and the output of this evaluation is yes or no. And then the voting of this network triggers the decision, and it can use these privileged EVM opcodes. And now it can freeze contracts, move tokens, run arbitrary privilege code, configure the platform, you name it. So how does it work? Well, people create neurons by making, guess what, another security deposit, and they do it because they can get rewards by doing this. So here's somebody, he's depositing DFINITYs, and he's getting a neuron, and now he's a controller of that neuron, right? And the neuron is installed on his laptop or wherever, using the neuron's key pair, could be on a smartphone. And the voting power of your neuron equals the voting power of the DFINITYs you've deposited. And you can't get the money inside the neuron out without dissolving the neuron, and dissolving the neuron takes 3 months. So you better make sure you don't make any or contribute to any stupid decisions, because if the blockchain nervous system makes a stupid decision, right, the value of your DFINITYs is going to go down. There's nothing you can do about it because they're locked inside the DFINITYs, right? You've got to dissolve the neuron to get them out. Sorry, locked inside the neuron. So kind of using the invisible hand of the market to make sure that the blockchain nervous system stays sane, right? Because if the blockchain nervous system becomes insane and makes stupid decisions, the owners of the neurons are going to lose money. So neurons follow neurons, right? So, a lot of the times people won't feel qualified to vote on proposals, or they won't have the time. And they can have their neurons vote automatically by following other neurons. And it doesn't matter what the graph looks like, but you're going to get something like this. You're going to get a core developer, researcher, investor, foundation, Reddit pundit, right? And people are going to follow them. And then these guys are going to follow each other, and you're going to get some kind of graph, right? Doesn't matter that there are loops. All works fine. Now, crucial thing to realize is that these follow relationships are configured on the client. Nobody, right, can know where they are because the follow relationships exist on the edges of the network on people's client software, right? So here's someone's laptop, and they've configured for policy proposals. They've configured a follow list. These are just the addresses of other neurons. For mitigation, for protocol decisions, this is things like, I want to change the protocol and change some parameter in the cryptography or whatever. So, you configure this, and it's kind of simple, right? When a proposal comes in, there'll be different kind of schedules for when the thing's got to be decided on. If your client, which is running the whole time, doesn't get a decision from you after a default period, waits. It gives you some time to make your own decision manually. But if you don't submit your own decision manually, it then goes to the follow list, and it'll look at the follow list. Like, has the first person in your follow list voted? Yes, follow. If not, back off. Have either of the first two people in your follow list voted? Right? If yes, follow. Otherwise, back off. Have either of the first three voted? And there are various other kind of voting strategies you can imagine, and these things are configurable. But eventually, through these automated follow relationships, the blockchain nervous system will cascade to a decision on proposals. So, what's good about it? Well, it captures the wisdom of crowds. The community expertise is incorporated. Technically, I call it opaque liquid democracy. Opaque because the follow relationships exist at the edges of the network. Nobody can know what they are. The neurons cascade to make decisions on proposals. Actually, one aspect of this is, I suppose, a bit like biological intelligence. It's non-deterministic, right? It depends on timing. It's highly resilient. The trust graph, the follow relationships exist on the edges, and they're unknowable. So you can't sort of kidnap or extort or influence the key holders. If you could analyze that. A lot of people have proposed creating liquid democracy systems which are on-chain. The problem with that is that if I identify who owns or controls some of these neurons, and I can see who's an influencer or who holds the key to a decision being made, and now maybe I can kind of influence them, bribe them, kidnap them, extort them, whatever. Or even worse, the government might not be too happy might decide somebody was responsible for a decision, or somebody might get sued. So let's imagine, you say no vice or violence on the DFINITY network because we're trying to create this kind of middle ground, this decentralized cloud. And you have all these carve-outs, right? And there's a kind of constitution that neuron holders agree to. And so let's say it says no gambling, but you can have prediction markets, right? Because prediction markets serve this kind of valuable role, right? Meanwhile, my friend Martin Koppelman comes along with his Gnosis, and he puts a prediction market on the system. This is going to be really useful. We're going to do predictions on elections, on weather, global warming. And then, 6 months in, right, or a year in, say, it's just a hive of gambling and sports betting. That's all it is, right? And so now someone in the blockchain nervous system says, hey, well, this is no vice or violence. This is just people, betting on soccer matches or something. Puts a proposal in, right, that this is a vice. This is a vice contract. We should freeze it, right? And the blockchain nervous system, somehow cascades to a decision, and you can trace it back to like 3 kind of key people in that graph, right? And then Martin Koppelman's like furious, right? You've closed down my prediction market. I was making so much money from that, and so what he does is he wants to sue the people in the blockchain nervous system, right? That somehow are in this trust graph and responsible for it. So it's very important that nobody can tell how the blockchain nervous system comes to its decisions. There are actually some timing analysis and stuff you can do, but it's still pretty good. And there's a good incentive system here. Everybody involved in making these decisions, everyone controlling a neuron, has definities locked in their neurons, and the voting power of their neuron is proportional to the definities they've locked up. They're getting rewards for doing this, but they can't get that money out without dissolving the neuron, which takes 3 months. And how the markets work in crypto. It's very volatile. I mean, the blockchain nervous system did a crazy decision, then the price is going to go down pretty quick. The BNS learns, the follow relationships are dynamic. It improves over time. If you've followed somebody on Reddit and then you realize, in your sort of audit log, oh my God, I ended up voting for this completely stupid proposal, you're going to unfollow, right? A bit like a social network or something, I suppose. Thought mining, the neurons earn money, and I think a lot of people will, do this and create these just for fun, right? Create these neurons. So the way it works is if you have a neuron, your rewards, like your thought mining reward, is proportional to the amount of definities locked in the neuron, factored down by the number of votes that you missed, right? But you can avoid missing votes by setting up follow relationships and making sure your software's always on, right? So final thing, this is kind of boring, but it is important, public-private interoperability. And so the reason we're able to do this, and there's a lot of people talking about this kind of stuff, but if you want to do it, you actually need to have a highly consistent network architecture, which is what we discussed with the probabilistic slot protocols based on threshold relay. You need to have networks that reach finality very quickly, right? So, internet network, this is what we're familiar with. We don't think about it much, we're so used to it, but it works very well. You have the internet, which is here in dark blue, and then you have local area networks, private local area networks, which are in light blue. And then we have these services. So we've got the big public service on the internet, and then we've got these other pieces of software, or maybe not services, on the local area networks. Services or softwares on the local area networks can interact via these services on the internet. It could be that everyone's logging into Gmail or connecting to the SMTP network or connecting to a financial exchange or whatever. And we're very happy with this architecture. This, though, is the current situation we have today with Ethereum. We need to change. Here's Ethereum, here's a public service on Ethereum, and then here are private chains using Ethereum software. Right? The businesses have created because they want to have privacy, just in the same way people create local area networks because they want to have privacy, right? So DFINITY, wants to return to the internet model where you have the main public network with public services, and then you have the private chains, if you want to call them that, private networks, and they have services on them they can call into the public services. You can't call from one private chain into another private chain, or it wouldn't be private, right? But you can interact indirectly, and you can build upon these services. So here's a simple example. Here's a private chain, here's a private chain, here's a public carbon credits exchange. And let's say that one service on one private chain is exporting a carbon credit and the other one is consuming it. It's very useful for these different private networks to be able to interact like this. Also, there's this idea that software on private networks can build upon the software on the public network, right? So here's some kind of fantasy Solidity code, right? And it's saying include DFINITY, which means main network, stablecoin, so on. What's actually happening now is inside the code, wherever you see a reference to these smart contracts, it's going to expect to see, to find them not locally but on the main network. So here we go. Let's imagine some huge company like Foxconn has got a corporate supply chain and invoice financing market for their thousands of suppliers. And they're notarizing invoices, and there are markets which people can invest in to finance invoices and so on. Fantastic. They're very happy with their private network. They don't want everybody in the world seeing what's going on. It gives them a bit more privacy. But guess what? There's loads of things that they might want to have. They might want to make payments. That requires stablecoin. That's expensive to set up. There's loads of, if you just do it the simple way, right? Like backing it, regulatory issues, arbitration. What happens if there's a disagreement between the trade financier and the supplier, right? These are disputes, and these disputes need to be resolved. But maybe there's a network of arbitrators on the public chain. Identity, another big one, right? Do they have to do this themselves? Haulage, maybe. There's a network of hauliers. In the future, maybe truck drivers, and most truck drivers are owner drivers anyway, maybe they're just going to connect up via some open public exchange, and you can hire them to do stuff, and they've got a reputation and so on. Foxconn, whoever it is, doesn't want to build all these systems, right? Why would they? But so long as we can do this integration, right, they can use these public systems as building blocks. And I actually think that's a new business paradigm. In software development, we use software libraries as building blocks. And here we're kind of we're incorporating, pre-existing business logic and communities of people and services and so on. Release schedule we've got now. So our objective at the moment is to just produce this first release, which is called Copper, which has threshold relay chain, which already will provide huge performance improvements. Blockchain nervous systems, so we can upgrade and so on quickly, which of course security deposits for miners. Something called state root only chain. I won't explain that, but we don't want to record all the transactions. Have you tried syncing Parity or Geth recently? It takes a long time, right? It's a bit of a nightmare. So that's not the way we would do it. Following Copper is a thing called Zinc, which is the private-public interoperability thing. Then, we'd love to do this by the end of 2017. Tungsten is basic state sharding, right? Basic validation. So I won't go into why we say basic, but sort of very simplified. Introducing this asynchronous model for cross-shard programming, which, by the way, doesn't require any changes whatsoever to the Solidity compiler. Unique state copy IDs, this is something I haven't discussed. It's a cryptography technique for ensuring that somebody's got a unique copy of the state. There's a lot of systems out there at the moment that have this problem where, Filecoin, like IPFS. The idea is that you keep a copy of all these files, because if you get challenged, you can prove that you've got the file and you can get this reward, right? The problem is that there's no way of knowing that all those computers in the IPFS network aren't really running on a single giant mainframe somewhere. There may be a replication factor of 1. All that data might be sitting on a single hard drive. So DFINITY, because we have to partition data storage between processes, and also, it's an unstoppable decentralized cloud, right? It's like essential to the property of, we have to actually know that the data is being copied, right? So the software developer will make decisions about the replication, but if they say this data has to be replicated randomly across 100 different mining processes, then it really does have to be replicated across 100 different mining processes and held by them individually and not placed on some kind of single mainframe, right? And a kind of con. And so that's what that does. Advancements in the BNS. This is interesting. So one of the ideas behind the DFINITY Foundation is the foundation will dissolve itself within 10 years. And that maybe is too long, maybe it should be 5 years, I don't know. But dissolve itself, hand over its funds, or as soon as it can, anything remains, to the blockchain nervous system. And the blockchain nervous system will make all decisions, right? The only reason you can't do it at the moment is because if you look at a kind of business strategy, it involves lots of decisions that are interrelated, right? And it's more complex, right? Whereas the blockchain nervous system, or at least in the simple implementation, just sees a queue of proposals and it just votes on them, right? Like a kind of conveyor belt. It's not really set up for that kind of more complex processing yet. Finally, lithium, which is where we really want to go. It's a full validation tree architecture, micro-sharding, more advanced economic models, ZK snarks and other privacy, and just, as you can imagine, a sort of wish list of things that someone like me would like to see. And that's it. That's DFINITY.